All right, we are ready to start setting up the distance system that we need for our joints to not stretch. And this is where things are going to start to get a little bit hairy, so I'm going to try to go as slowly and carefully about this as possible. So there's several things we're going to need. The first thing is we're going to need all of our joints that are affected by the path constraint, not affected, but under it. So let's bring them over here. There they are. And they have their respective constraints with them, which is something we need to. We don't need the scene, so let's hide that. So let's try to order this as much as possible. So this is spine 01, spine 02, 03, 04, 05, 6, and 7. Now let's find their path constraints. There's one over here, one over there, this one, then we have this one, this one, and this one. There we go. So let's move these guys closer. What we're going to do is we are going to change one of the parameters on the constraint that determines where on the curve that locator is. And there's actually two parameters on the path constraint that do that, which I'm going to show to you in a second. If we select one of these constraints over here, you will see that they have a path offset and a path percentage. So the path, they do basically both do the same. The thing is, when you constrain something with compensation on, usually that value goes on to the opposite. And right now they're holding pretty strange values. Like this guy went to a 600%, which is not true, but it's 100%. But for some reason, Modo determined it to be like that. So for example, you can see that the other constraints are, this guy is 83.4514% along the curve. This guy is 66, and so on and so forth. Now, you can still use a path percentage to drive that object along the curve. But the path offset allows the object to stay at a certain percent along the curve initially. So you can animate the percentage from there. We're not going to be animating these constraints, obviously, but you can do that. So what we're going to do is we're going to drive the offset procedurally through some nodes that we're going to add over here. And those nodes will determine if the object is supposed to scale, well, not scale, but move along the curve as the curve is stretched, or stay at a given position. So we're going to do that. But to do this, we're going to need this offset channel as part of the node. As you can see, it's not there right now. So I'm going to select all the constraints and right click on one of them and say add channel, and we're going to look for the offset channel, and it gets added to all of them. I'm going to have to reposition this a little bit because I have not added this earlier, so let's just move them around so we can see better our constraints. Let's just leave them like that for now because we're going to keep adding more channels later. So now that we have the offset, what are we going to do with it? Well, we're going to change where in the curve these the spine joints are. Okay, so let's do just that. The first thing we're going to need is we're going to need some nodes that represent normalized indices or a normalized index number for each joint in the chain. What this basically means is if you see our path percentage and offsets are in percent, so it goes from 0 to 100%. So I want numbers that match exactly this on a per joint basis, representing a point on the curve on which each object would lie. But I want this in a 0 to 1 range. Okay, so we're going to create some nodes that are going to act as placeholders for these values. So let's do, I'm going to add just math nodes. We're going to use ath nodes. And these are going to be one per joint. I'm going to put them over here. So we're going to need 7 of these. So let's I'm going to just be duplicating them. 3, 4, 5, 6, and 7. Okay, now I need them to have float values that go from 0 to 1, evenly spaced. So to do this, I need to divide 1 by the number of nodes that I have here, minus 1. Why minus 1? Because the first one is going to be 0 always. So I'm going to do that in my trusty Windows calculator. Let's just divide 1 divided by 6. So we get 1.6667. It's not going to be an exact value, so it's going to be a little bit hard, but well, we'll deal with it. So the first value needs to be 0. The second one is going to be that number, 1.6667, let's say. Okay, I think Modo doesn't do more decimals, so yeah, that's it. So let's copy this guy and go to the next one and do this times 2. Okay. Oh, it's not 1, it's 0.1. 0.1667. There you go. Just copy this, come here, paste it times 2. In the next one, paste it times 3. Here it's going to be times 4. Times 6. Oops. Looks like we reached 1 sooner than expected. This is times 1 times 2. Did I miss something? This is times 3. Yeah, we're not supposed to have a 0.5 value anywhere because, oh, actually, yes, we're supposed to have 0.5 here. So this is times 1, 2, 3. This is times, maybe I skipped one, times 4, times 5. Oh, there you go. Times 6. Well, this should be just 1. Let's get rid of the there you go. So these are our, let's say, normalized values along the path of the curve. Okay. So now we have that. Now I could just plug these in directly, and it would give us exactly the same result we're having now. These joints would just stay at those positions along the curve, and as the curve stretches, they would keep that percentage, and they would stretch with the curve. But we said we want to keep them static. But by static, I mean as the way this is going to work, if I can explain it better, is as the curve stretches, each joint is going to figure out how much the curve is stretching, what's the difference between the length of the new stretch value against the length of the original curve, figure out the difference, and then he's going to move back on the curve that amount, therefore keeping its current position on the curve. So it's going to be basically negating the stretch on the curve. So we are going to need a few things to get that to work. We need to know what's the length, the default length of our current curve, and we also need to know the length of the curve at any point in time as it stretches. Okay, so we're going to get those two values using a new feature in Modo 8. It can also be done in previous versions. I'm going to explain to you how, but I'm going to take advantage of the new feature because it's nicer to use, which is the probe. I'm going to use a curve probe. So the curve probe node, it can basically take information from any curve you plug onto it. And one of the channels that it allows us to read is the length of that curve. So that's the way I'm going to get the length of the curve at any point in time. So I just add the curve probe node, and I'm going to take my curve object and plug it directly in. And now the curve probe node is going to read information from that curve. As you can see, if I go to my channels, the length is still at 0. It doesn't give me anything. And that's because for this node to work, it needs an input position, which basically is the actual purpose of this node would be to get the closest point along the curve for any position in space. So you could have any locator close to the curve or on the curve that is not necessarily constrained to it, and then use that as an input position. But for the purpose of this rig, we actually don't care. We're not trying to use this node for that purpose. But the node still requires that that input position. So I'm just going to feed it 0. I cannot type a 0 into this channel because, as you can see, it's a matrix 4 type of channel. So there's no way to type a matrix 4 anywhere here. 0, I mean, for a matrix 4 value there. So I'm just going to have to create another node. And in this case, I'm going to go to matrix, and I'm going to use a matrix construct that basically takes a vector and converts that into a matrix that I can feed anywhere. For a vector, I can type 0 values. So that's what I have right now. I'm going to leave it like that. I'm just going to plug this into the input position of my curve probe. And now you can see that I have a lot of information here. The one that I'm actually interested in is this length value. That's the only thing I want for now. So that's the current length of the curve that I created for my spline. Okay? So it's 420.6. That's it. So the first thing I'm going to do is I'm going to copy this value. Well, I can't copy it from here, but I'm going to create a new math node. Yeah. And I'm going to take this value, 420.6001, and put it here. Okay. And I'm going to call this, let's say, utility center spine curve length. Okay, this is the original length of the curve. So what I need to do is figure out what is the difference between the length of the curve at any time. This is going to update as you stretch the curve against this guy. And how do we do that? We just divide them. So let's create a math divide node, and we're going to divide the length of the curve as it changes against the original length of the curve. And this is going to give us more or less a ratio that tells us how much the curve is changing. So right now, the result of this should be basically 1. It is not, because my first value, it's being taken, this guy is being divided by 100. So I'm going to change this to reflect that. So my value is going to be point. There you go. And now we have 1. Okay. So that's what we need to see over here. Okay. So now that we have this, we need to figure out how to move the joints in the chain depending on the change of this value. Okay, let's rename this to UTI center spine stretch percentage, something along those lines, okay? And these are, I already said, my indices for each joint. So what we need to do now is we need to make sure that each joint is kept in the same order. So that's why we created these indices over here. So we need to divide, again, the index for each joint against this number that we just got, okay? So let's create another divide node. And we're going to divide the bone index by the number we just got. So let's start, for example, with the first joint at the bottom. We know that he is at 0 on the curve right now, so we're going to take the 0 index. Well, I call it 0 index, but it's the first node representing a joint over here, which is value, it's 0 right now, okay? So right now we have 0 value, and then we have the 0 divided by something. It's going to be 0, so this joint will effectively never move, but we're still doing it for him, just to show you how this is going to work. And then we're going to have to repeat that for each and every joint on the system. So now that this is set up, we can just take this value, and we're going to multiply it by something else. And this is where the weighting system is going to come in. We're going to use two values, one to either stretch the spine or not stretch it. And we're going to use something very similar to what we've done before for the IK blending, which is a 1 minus 1 system. So let's create another math add. And we're going to create a subtract. And this guy is going to be 1 minus whatever's coming from this guy. Okay. Right now I'm going to set it to 1. And this guy is going to be our no stretch weight. Okay. So when this is 1, the spine will not stretch. When this is 0, it will. So let's call it UTI center no stretch weight. And we're going to call this guy UTI center stretch weight. Okay? Okay, so far so good. So what we need to do is now multiply the result of this division by this number over here, by the weight of the stretch, because this is what's going to actually move back the joints. Okay? So let's add a math multiply. And we're going to take whatever's coming in from here and multiply it by this. Okay? Now, we now need to figure out what to do when we want the spine to actually do stretch. So we're going to need to multiply another set of numbers. So let's add another multiply node. We're going to put it right here. And this guy, since we want to keep the actual offsets that we have right now, is going to take the same position index, I might call it that way, and it's going to be multiplied by the stretch weight. Okay, so when this guy is 1, you're just basically going to get this position along the curve, and that's it. Okay, and now that we have both working, we just need to add them. So let's do a math add. We add both values, and this is our offset for this joint in the chain, which is going to be spine 0, 1, if we are correct, because this guy needs to be at 0 on the curve. Let's find him. Yeah, spine 0, 1, which is here at the bottom. So we need to connect this to this offset. So let's take all this, and you know what? To follow the same order I have here, let's reorder these guys. Let's put this guy at the bottom, this guy at the top, this guy over here, this guy over here, Then we have this guy over here and this guy over here. Why is this guy 4? Let me check that out. So this guy 0, 0.1667, 3.5, 4. Yeah, this is not correct. I think I must have typed, I wanted to type times 4, but it just entered 4. So let's copy this number again. And let's go here and enter it. Times 4. Okay, there we go. That's better. Now that we reflect in the same order, we can take these nodes and let's bring them over here to the spine 0, 1 constraint, and we plug them to the offset value. And this guy, he won't move. But let's try that on the last joint, which is over here, and you'll see what's going to happen. Now the easiest thing to do is going to be to take these guys, just duplicate them, and now I need to delete all the inputs that they currently have. So let me just see, this is in the front, this guy should be here, this guy should be here. Okay, so yeah, I'm just going to unplug. This guy needs to stay, this guy needs to stay. We need to unplug these two sockets with the index coming from 0. And we're going to take them from the last joint in the chain, which is weighted to 1. From him and over here. And let's take this assembly and move it over to our last constraint. And plug it to the offset. So nothing is happening right now. However, let's see what happens if I move this control. As you can see, the head is staying in place over here. And that's because the last joint in the chain is not stretching anymore. It's staying in place. However, if I take this value over here, which is our no stretch control, and I bring this down to 0, you can see that the head moves back to the end of the curve. So there you have your stretchy spine against non-stretchy spine. Okay, don't go beyond 1 on this guy because it's going to continue to move down. And there it is. Now we have to copy the same thing over to each constraint and plug it to the right bone index. So let's just do that. Let me just undo everything. So there you go. We're back in place. Let's go back to setup mode and let's do the next constraint over here. So we're going to take these guys, duplicate them. Let's reorder this again. This guy goes in the front. This guy goes here. This guy goes here. And let's unplug this socket. And which one is coming? This socket. And these guys have to come from the next node over here. So we plug that one in, and we plug it over here, and we plug this into our offset. And oops, what did I just unplug? I unplugged the mesh. Yeah, sometimes you gotta be careful with what you touch when you're in the schematic view. I'm just gonna bring these guys closer. This is starting to become a little bit of a mess, but well, there's not much you can do about that. Let's keep on going. Let's now do the next joint. So let's take these guys again, duplicate them. Let's move them down here. So we need to have the add in front, then this guy, and then these two guys. And again, we need to unplug this socket I'm holding down Control and just touching the socket to unplug it, and this one. And we wire up the next index, and we wire up the offset. There you go. And we are just going to keep on going, duplicating, and ordering properly. And we need to unplug this socket and plug the next one. All right, and we have 2 more to go. Let's duplicate this guy. This guy goes here, this guy goes there, this guy goes behind. And again, unplug here, unplug there, plug this guy, plug to the offset, and last one. And unplug here, and we plug the next joint index and plug to the offset. All right, we're done. So let's see how this works. I'm gonna lay this out a little bit better in a second. I just want to see how it works. So let's go down here to the actual node that is going to control the entire behavior of the spine, which is this guy. So right now the spine is set to not stretch because its weight it's at 1. Let's see what happens. We're going to grab our control and move it. Oh, of course I need to get out of setup mode. See? Our spine is not stretching anymore. It's keeping its length, even though I'm stretching the curve quite a bit. So it's figuring out everything properly. Now there is one thing that you need to consider for this setup. If instead of stretching the curve you contract it, the bones start to collapse on one another. You will see that they just group together at the end of the spine. So this is just a side effect of how this setup works, and there could be another mechanism to actually get them to stretch down, but this is supposed to be a non-stretchy spine, so we're going to leave it at that to not complicate things more. Now if I take this basic math node and set the value to 0, now I can stretch my spine all I want. And it stretches down, stretches up, everything is good. So there you go. That's how you get a stretchy against non-stretchy spine. Okay, so let's leave it at that, and we're gonna continue with the spine setup in the next video. Okay, before we move along any further, I wanted to stop for a second here and take a look at the math of what we just did in case it was not clear enough. So we basically have 2 different setups going here for the movement of the joints along the curve, and then we add them both together, and that gives us final result because both systems are weighted, and they are weighted in an inverse manner, where if one system increases its weight on the final result, the other one decreases it, and vice versa. So let's take a look at how they work so you can better understand why we did everything that we did. So let's start with the simple one, which is a stretch spine setup. This is actually well, basically the system is almost not a system at all. I'm just passing the original joint position along the curve. That's it. That's my stretch position, is a joint position along the curve, and that comes from these numbers that we created initially over here, which are let's call them normalized segments along the curve for each joint. So your first joint will be at 0 on the path, 0%. The next one at 17%, 33, 50%, 67, 83, and 100%. So that's all I'm doing over here. I'm passing that as a joint stretch position. The only thing I'm doing is I'm multiplying it by the stretch weight. And I do that because, as I said, we're dealing with two systems that are weighted. So I need both of them to have a weight. So basically I multiply this by its own weight. So for example, when you're using the non-stretch spine setup, this weight would be 0. So when you multiply this position by 0, then this system is deactivated, basically. Now the one that is a little bit more complicated is the non-stretch spine setup, because this one, what it's basically doing, it's using the path offset spinner to move the joint along the curve. So what it's doing is basically moving it back or forward. Well, not forward. It only works backwards. It's moving the joint backwards on the curve as the curve stretches by the same amount that the curve is stretching. So the effect is that that apparently the joint does not move in space, in 3D space. It's just moving along the curve in the same amount that the curve is stretching. So we figured that out, but first you have to get the stretch factor, which is how much is the curve length now greater than its original length. So basically you take the existing length at the moment of the evaluation and you divide it by the original length, which is a static value. We get that one from when we start the rig. And the result of that's your stretch factor. That's how much the curve has stretched against its original length. Then we take the initial position of the joint on the curve, which is again these numbers we got right here, and divide that by that factor, and that tells us how much the joint has to move. We have to do this because you have to remember that these movements are relative to the current position of the joint on the curve. You cannot compute them starting from 0 because then all your joints are going to collapse. So you have to take into account the current position of the joint on the curve. So that's what we're doing over here. And then basically we just take that new value, which is our new position on the curve. That's basically where we stop calculating the movement of the joint. And we just multiply it by the weight of this system so that we can have the final non-stretch position. Obviously, when the non-stretch IK is set to 1, well, this takes full weight. Otherwise, it starts to be weighted against this other value we computed for the original position, which is just this pure number here. And finally, adding both together gives us the final setup, the final position for the joint, taking into account both systems. So that's how it works. It's really nothing more complicated than that, as you can see. Now, as you might have realized at this point, this setup gets pretty complicated visually. It makes our schematic pretty busy. So one thing that we can do to try to clean this up would be to use expression nodes. And the advantage to the expression node is that we can include all these operands inside of the expression, and we would not have these many nodes outside. We would just have one over here. The caveat we use in expression nodes is that they only accept 4 inputs. So we need to figure out if we have 4 values maximum that we can pipe into the expression. If we have more than that, then we cannot use it, at least in this example. So let's see if we can simplify this to work as an expression. So let's say that the curve stretch factor is going to be equal to the original length divided by, that's the present length divided by the original length. Now these two need to come in. These two need to be variables for the expression because they're coming in from nodes that we have over here on the network. So this is our original length, and we're getting this divided by this. However, since this part is calculated outside of the, or where the expression node would be, we don't need to take those into account as variables. We can just take the result of that, which is this one, and this would be our first variable. So let's call this one A. Okay, that would be the first one. Then we need to take A and divide it by the position of the node on the curve, which is this number here. So that's going to be our B input, which is going to be, let's say, the joint change percentage. It's going to be equal. We don't need to write this in the expression. I'm just using it for reference. It's going to be the joint curve percentage. Let's call this here V percentage, and this will be our B variable divided by our A variable. Okay, the stretch factor. And finally, we'll multiply that by the stretch weight. So joint non-stretch position is going to be equal to the joint change percentage multiplied by C, which is the non-stretch weight. Okay. And then for the stretchy spline, the joint position is going to be the joint position along the curve, which we've already used over here. Where was it? I think we called it joint curve percentage for the purpose of this. Yeah, it's the same value. So we're gonna reuse that. It's going to be, let's call it joint stretch position. It's going to be, and in this is B, the variable B joint curve percentage multiplied by D, which is the stretch weight, and that will give us our final result. So apparently we do have the possibility of using expressions because we only have 4 inputs so far, A, B, C, and D. So let's see how we would write this as an expression. So as an expression, this would be, we have here the non-stretch position plus the stretch position. Okay, we're gonna substitute these in a second, and this is gonna be final joint position is equal to this. Okay, so this is what we're doing over here. So let's start with this one, which is actually the easiest one to do. So we said the stretch position is going to be our joint position along the curve, which is B, joint position along the curve, or percentage, times the non-stretchy weight, which is C. Right? Good. Now let's look at the at this one. So on this one, we have to take the curve present length and curve original length and divide that, and it gives us a stretch factor. But we have already over here. Actually, we might need to include that in the expression node. So let me see. Here we have the original length divided by the current length. Okay, it's this guy who holds it. This is our first input, the stretch factor. Okay. Yeah, it's here, the stretch factor. So that's being divided already. We don't need to include it in the expression. So then we say the joint change percentage is the joint curve percentage, which is our B input divided by this. So let's do that. This is going to be B joint curve percentage divided by A, which is the stretch factor. Okay, and then we take this, the change percentage, and multiply it by the non-stretch weight. So we're going to take this and multiply it by C, the non-stretch weight. And this is going to be the expression we're going to need to calculate to get the same result that we're getting from all these math operands. So let's try that out. Let's see if it's going to work for us. So we're going to go add an expression node is on the other category. Here we have our expression node. And I'm going to try it out on the topmost joint on the hierarchy, because that's the one where it gets easier to see if the system is actually working when I move the control. So as you can see, the expression node has 4 inputs, A, B, C, and D. And then here you write your expression. Okay? So we need to wire things up. So we said input A is the curve stretch factor. So I know that's being stored in this division operand over here. So let's plug that to input A. Okay? So now we have that. Then input B, according to our expression, let's make this smaller, needs to be the joint curve percent value, which is held by this number over here. So let's plug that as input B. Then we have input C, which is the non-stretchy weight, and input D is the stretchy weight. So C and D are coming from these nodes over here. This is the non-stretchy weight, and this is the stretchy weight. So we said C is a non. Okay, so this guy is going to be C, this guy is going to be D. So let's plug those guys into the corresponding channels. And this guy is input C, and this guy is going to be input D. There we go. Now we can write our expression. And since you cannot write names into the expression itself, all you can use is the A, B, C, or D inputs. We're going to write this down as the following. It's going to be B divided by A times C plus B times okay, this should be the stretchy weight, which is, what did we say? D. Yeah, I made a mistake over here. B times E. So that's the expression we want to enter into Modo. So let's just copy it and paste it over there, and that's it. That's all we need to do. So let's see if that's the case, that this actually works. So I'm gonna unplug this from there and just wire in the output, and let's see if it works. Let's make this smaller, grab our control. Let's see what value we have right now for the stretchy spine. Right now the stretchy spine is at 0, so the joints should not stretch. Oh, sorry. 0 is at the non-stretch is at 0, so it should stretch. So let's now put this at 1. And yeah, our expression node works. So we can go ahead and replace all these math nodes with a single expression node. So you can, for example, just take these guys, delete them, and leave this guy over here. And all I'm going to do is, because the inputs and the expression are not going to vary at all, is I'm just going to duplicate him several times and unplug stuff, plug it in, and take those nodes delete. Let's duplicate him again. Let's unplug that socket, plug it in. You can also just plug things directly if you want. Let's move these guys up because we're not going to have enough space for the ones underneath. Duplicate this guy. You can just also drag the wire directly from this guy and replace the existing connection. But I'm gonna do this a few more times. I need to obviously replace these inputs later on the nodes that I just duplicated, because right now they're all taking the same position index value, so we don't want that. We need to correct that. Get rid of those guys. So let's get rid of this guy. And oops, select first, then duplicate. And this guy. And we can take these guys, delete, and move those back. And now we can replace, this guy is input B on all of them. So let's do that. Input B. And let's wire in the correct one. So this guy is going to be on this node. This guy is going to be on this node. This guy on this node. This guy on this guy. There you go. This guy here, and our last guy over there. So that's, well, better. It's still noodly, but well, that's just how setups work. So let's test it out to make sure everything is okay. Yeah, non-stretchy spine. Let's go to our math node. Change this to 0. Stretchy spine. So we're good. At least we have less nodes to get lost in there with the expression, which is better in this case. And one thing to be aware of is I'm not sure if there's any difference in Modo, but in some other 3D softwares, sometimes expressions are slower than actual math nodes to evaluate due to the parsing of the expression and stuff like that. But I don't know if you ever see a difference where having multiple rigs in a single scene makes them slower. Try maybe replacing your expression nodes with actual math nodes and see if those new rigs make up any difference in performance. But so far our rig is looking okay. So we're gonna leave it with the expression nodes, and I might rename these later to something more meaningful, not just expression. You know, we've been using the UTI prefix for nodes that are meaningful in the schematic view, so we might do that. And before I finish this video, I just wanted to mention something that we failed to check when we were working on the spine setup before, and that's when you do the path constraining of your joints onto the curve, one thing you want to probably do is make sure that on the constraint itself, let's grab, for example, this guy. Let's go getting path constraint node. That the axis that is selected for the constraint is the axis that you set your joints to run down the the length of the bone. So for example, right now, well, actually in this case that didn't have any effect because I had compensation on. So even though the axis for the constraint is set to be the z-axis, my joints are still facing on x. So that's okay. It just means that that there's a rotation stored in the offset to maintain the orientation of the joints. But it's something that you might want to keep in mind. Like say, it's if I replace here for x, I'm gonna be more consistent with my setup. So let's do that. I'm gonna set this as the x-axis. Now I have a flip over here. So I am actually not gonna fool them with this. I'm gonna leave it as it was. So yeah, I just wanted to make sure that you're that you keep an eye on when you assign path constraints and stuff that changes the rotation of your objects. Just make sure, go back and check the orientation of your joints to see that your rig has not changed in any way. So that's pretty much it. We're done with this part of the setup. Let's continue because we're not done yet. See you in the next video.